Are we on? All right. Hey, good morning. It is Wednesday, April 1st. It is April Fool's Day. I hope you guys are all doing well. And as promised, here is another class. We're going to keep doing this. Just for you guys to know, the notice from CPS came out earlier this week, and we are moving to remote learning, which has some other connotations associated with it, but basically we're going to be continuing on class officially. We're going to be kicking off those things after the spring break. So we're going to finish up these activities here this week, and then next week I will be off for spring break, but if you guys need anything, you can always reach out, and I'll be on email, but we won't be doing any more class time or assignments for next week, but we'll just be sheltering in place and enjoying time with our family and hopefully staying well. But then after that week, we'll be coming back, and until we get notice that we get to go back into the school building, we'll be keep doing this. So anyway, I hope you guys are doing well, and today we're going to talk about masses on springs and the simple harmonic motion of things that bounce and go back and forth, like Homer here. So let's get started. So a mass on a spring is another motion that models simple harmonic oscillation. So you can see here on the that's fun. In the upper right corner of your screen, you can see there's a mass on the end of a spring, and it's bouncing back and forth and back and forth. And you can see that, here, I'm going to move the mouse here. So the middle point of the spring is roughly right here. So that's what we would call the equilibrium point for the spring. And it moves back and forth just like the pendulum on the end of a string. So and the equations for period and frequency are exactly the same. I know my head is blocking the frequency, so I'll duck here. Right, so the period of time is the time for one complete cycle. The frequency is the number of cycles per second, or the number of cycles per unit time. And then frequency is equal to 1 over period. We can also say that period is equal to 1 over frequency. And so if we were to look at this model right here, we can watch the clock here and see how long it takes for it to do one full oscillation. So let's see, I'm going to start it. So that was where it started. And then when it comes back, that's about 8 seconds, right? So it goes back all the way back to here, 16, right? So looks like the number of cycles per second, or here in the graph we could count. So that's down and back up. That's 1 full cycle. Down and back up. That's 2 full cycles. Down and back up. That's 3 full cycles in 24 seconds. So this should be a review from the last homework assignment as well. So, but let's take a look at what this means in terms of springs. So, springs are defined by a thing called their spring constant. So, lots of different springs out there exist. You've got these little small light springs, you've got these thick heavier ones, and these ones in the middle. So, we refer to springs by what we call their stiffness, or the resistance of change, how much force is required to squeeze or compress it. And that is called the spring constant, and it's represented by the letter K. So the spring constant K is in units of newtons per meter, meaning how many newtons, how much force is it required to compress it, or also to stretch it by 1 meter. So if you have really weak springs, some light ones that we have in the classroom, those usually have spring constants of anywhere between 3 to a few hundred newtons per meter. The shocks in your car. The shocks in a car are generally measured upwards of 150,000 newtons per meter. And you can imagine that your car springs don't stretch a full meter. They move maybe up and down a few inches, and it requires quite a bit of force to compress that all the way down. And so that's just an example of how we define springs. So now when we graph the force versus the stretch, or the force versus displacement of a spring, you see something like this. And you get this nice linear response. That as we stretch that spring more and more, the force on that increases linearly. You'll notice too that the slope of this is a negative slope. And the reason why it's negative is that as I stretch it this way, the force that's applied is in the opposite direction. That's why we have this negative symbol. And this is what is called Hooke's law. They often refer to springs as being Hookean, which means that they are linear. As I stretch it, if I stretch it 1 meter, requires so much force. If I stretch it 2 meters, it requires twice the amount of force. If I stretch it 3 meters, it requires 3 times as much force. And we generally don't stretch things a full meter. We usually just stretch them a few centimeters, but that relationship is linear. And the constant K, this is that spring constant that we talked about before. So big springs have a really big K value, and small springs have a very small K value. It's what we call Hooke's law. So there's an equation that gives us the period of a mass on a spring, and it's very similar to the equation that we had for the pendulum. This one is T is equal to 2 pi times the square root of m over k. T is the period in seconds. Mass is measured in kilograms, and k is the spring constant in newtons per meter. So if we were to look at this spring here that's oscillating back and forth, and we were to try to determine this period of it, we could either watch it, right? We already saw that it was 8 seconds, but we could also look at it in terms of what is the mass, and on this simulation we can see here the mass is 3.3 kilograms, the spring constant is 2 newtons per meter, and when we take 3 kilograms divided by 2, take the square root of that, multiply by 2 pi, you get 8 seconds. So we'll do some equations and problems like that in the homework that I assign here. And the last thing I want to talk about is this concept of what we call undampened and dampened oscillations. So and we'll see if this gets flagged by YouTube, because I scraped this straight from YouTube, but I did put the clip credits right here. So an undamped oscillation is one that goes on and on and on forever, right? You'll notice that the amplitude stays exactly the same. It swings, if it starts on one side, it swings back, and it swings to exactly the same height. But we know that in the real world, there are things like air resistance and friction and dissipated energy. And so in the real world, you have what is called a dampened oscillation, where that amplitude, that swinging, gets smaller and smaller and smaller. So if you've ever had little brothers or little sisters, or you yourself have been pushed on a swing, right? You swing, and in order to keep swinging, something has to keep pushing you to keep that motion, and that's because there's energy dissipated. That is what's called a dampened oscillation. And what I want to point out here is that if you look at this animation on the right, you can see that it's oscillating, and the amplitude is decreasing, right? So the amount it swings back and forth is getting smaller and smaller. However, the frequency and the period stay exactly the same. So if I look at the time that it takes for it to do one full period, that period maintains the same. And that's something that we learned before, that the amplitude, or that the period is independent of the amplitude, right? So it doesn't matter how big the swing is, that amount, the time period it takes to swing back and forth is always going to be the same. So we could look at the same thing with a mass on a spring. This is what it might look like. And that energy, right, as it's stretching back and forth, is getting dissipated. The spring itself is probably heating up a little bit every time it gets stretched a little bit, right? And it doesn't spring back to exactly the same amount. Now, we're not going to do any actual problems that involved dampened or undampened oscillations, but I just want to make sure that we cover this because it's kind of more common of what you'll find and see in the real world. We don't have frictionless environments or areas or things that go on and on forever and ever. So one of your activities, your homework assignments, the last part of your homework this week is going to, again, to go to the FET site and to do this activity where we are going to explore masses on springs. And so I just want to walk you through kind of what this simulation looks like. So I'm going to open this up. And we're going to click here. And click intro. And in this environment we can do some fun things. We can take a mass, we can hang it on the spring, and we can watch it oscillate. And if I click stop, I can now change the spring constant. I think in the homework assignment I wrote for you guys, I asked you guys to change it all the way to the smallest and then all the way to the largest. And then first find out, we're going to do just like we did with the pendulum lab. We're going to start the stopwatch. This one, the stopwatch is over here. Click play. I'm going to click start. 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right, so that's 10 full oscillations. I think I actually asked you guys to use a different mass, but that's how you'll do that part. And then the last part is if I wanted to actually calculate or find out that spring constant, there's a couple things we could do. And we know that when I take this mass, if I take a small mass and I hang it on here, and we have to make sure we're playing here, so I'm going to click stop. So this is what we call the equilibrium position. And the natural length, I don't know if you saw that, what I did was I clicked up here. Natural length is the natural length of the spring without a mass on it. So right now, we have 50 grams hanging on the spring, and it has stretched this amount. And so if I wanted to find out the amount of stretch, I grab the ruler, and I place it right here, and move that there, right? And it looks like, what is that? Okay, so that should help 15, you with most of the homework. There are some other problems that involve using the equations. Maybe. But quick 16 summary of the notes here. Looks like it's in centimeters. So simple pendulums, so 0.165 meters. Remember that the period of time is equal to 2 pi times the square root of L over the
G.
The force period is only dependent down on here. 50 grams.
So depending,
it's not 50 grams
planet
you are
on,
there,
if you're on the
but
moon,
it's 50 grams
Jupiter
times 9.8. And the length of that pendulum
go back to
are the only things
here.
that matter or that affect the period.
I don't.
The mass on a spring, the equation looks really similar, but instead of 2 pi times the square root of L over G, this is 2 pi times the square root of M over K. And the period is dependent on the mass and the spring constant. So, and here has no effect on the length, right? So the length of the spring doesn't matter. Gravity also doesn't matter, right? So this doesn't matter whether you're on the moon or on Mars or on Jupiter, right? For a mass on a spring,
what we have here
matters is
we
the
said
mass
that
and
period
that
of
spring
time.
constant.
Sorry.
And in both the scenarios, I'm blocking that, but in both scenarios, amplitude has zero effect, right? So it doesn't matter if it's a big oscillation or a small oscillation. It is exactly the same period of
You know that the force pulling down on this.
That's it. I hope that was helpful, and yeah.
M times G.
Take a look at
So in
the
this
homework
case,
assignments. This will be the
we
last
wanna use
assignment that we
not
have for
50
this
grams,
week.
but in
And,
kilograms, 50 grams
and
is
then
equal to
I'll probably post another short video
0.050
going over a few of the problems
kilograms,
tomorrow
right?
to help you guys out.
And so,
And then
this is
another short quiz on Friday. And then after that,
0.050
we are
kilograms
officially off for a
times
week for spring
9.8
break. It's not going to feel like much of a spring break, but anyway, I hope that you guys are
do that.
staying safe and being well.
0.05
And, I do miss
times-
seeing you all, and it's awkward
0.05
talking
times
to
9.8.
a screen and a video here.
Which is
But
0.49.
anyway, I hope you guys are doing well, and I will see you guys soon. All right, bye-bye.
0.49 newtons.
And the stretch. Oh, what was the stretch on that? We said the stretch was 16.5 centimeters. And we know that delta x is equal to 16.5 centimeters delta x. And that's equal to 0.165 meters. And so if we were to graph this, we could graph it. We could also just, we also know that 0, 0 is one of our data points. We can just find our k value. We know that f is equal to k times x, right? So if I want to find k, all I have to do is divide f by x. And so in this case, it's 0.49 newtons divided by 0.165. Right? And 0.49 divided by 0.165 gives us 2.97. 2.97 newtons per meter. Oh, that's getting a little messy there. But that's one of the things that you'll have to do